In my previous video where I demonstrated the parametric VaR and conditional VaR using the Gaussian distribution, okay, we use these formulas to calculate VaR and also conditional VaR. If you would like to incorporate skewness and kurtosis into the estimation of VaR and conditional VaR, then you can consider the Cornish-Fisher expansion, okay, where we can actually incorporate skewness and excess kurtosis k here into calculating the standard normal variable. So of course, if the formula for VaR and conditional VaR is still mainly based on the mean return plus the standard normal variable, I'll denote it as W now, okay, multiplied by the standard deviation. And of course, the alpha or the significance level will determine the standard normal variable. So we will first start off with the standard normal variable Z based on alpha, and then after that, the next three terms here will incorporate the skewness and also the excess kurtosis. So excess kurtosis here is the kurtosis minus 3. So if, let's say, the distribution follows, let's say, a normal distribution, which means the skewness is 0 and the excess kurtosis is 0, then we will just fall back to the parametric VaR that is based on the Gaussian distribution, which is based on the previous video. For conditional VaR, we will use the same basis, but the cumulant or the standard normal variable now will be based on the initial formula, okay, which is 1 over alpha times 1 over square root of 2 pi times the exponential of negative half times the standard normal variable squared. Okay, but then we will have to scale it based on the skewness as well as on the excess kurtosis. So we'll now start to build this into the Excel worksheet. Right, continuing from our spreadsheet, I'll now label the new section, okay, as the modified VaR and conditional VaR, and this will be based on Cornish-Fisher expansion. So of course, apart from the mean and standard deviation, we will need the skewness and also the excess kurtosis. And we can compute this from our data. So the skew here will be based on L3, okay, our return series. And then kurtosis is based on kurt, okay, then based on L3, the return series, but don't forget it's excess kurtosis, so we need to minus 3. Okay, so what we can observe here is that the return series is positively skewed, and it has a positive excess kurtosis, which is a leptokurtic distribution. So in other words, there's fat tails. Okay, now we'll proceed to compute the VaR, but before that, we will need to calculate the standard normal variable for the VaR, assuming that we incorporate the skewness and kurtosis based on Cornish-Fisher's expansion. So let's start. So we'll take the cumulant from our previous part, which is in this case O11, and then we'll incorporate the Z squared minus 1. And then we'll multiply by the skewness, divide by 6. Okay, and then we will add in the Z value times the Z value squared minus 3, then multiply by the excess kurtosis, divide by 24, and then we'll minus the Z value again, okay, multiply by bracket 2 times Z to the power of 2 minus 5, okay, and then we'll multiply by the skewness to the power of 2 over 36. Right, so we're done. We have the standard normal variable now, and then we can proceed to calculate VaR, which is negative multiplied by the mean return plus the standard deviation multiplied by this adjusted standard normal variable. So our VaR here will be in positive terms, that's 7.428%. We should notice is much greater than the VaR that we computed previously, assuming a normal distribution. And this is to be expected because we have now incorporated skewness and the excess kurtosis into estimating the VaR. And then for conditional VaR, we'll calculate the adjusted standard normal variable. So for this case, I will take the Z, the uppercase Z that we calculated previously. This is the Z value for the conditional VaR. Okay, but then we will need to scale it for Cornish-Fisher's expansion. So this will be 1 plus the Z value times the skewness, divide by 6. And then we'll plus 1 minus 2 times the Z value to the power of 2. And then we'll multiply that by the skewness squared over 36. And then we'll plus negative 1 plus the Z value squared. And then multiply that by the excess kurtosis over 24. Okay, so we have all we need. So that's our standard normal variable here. That is for the location of the conditional VaR. So this is our conditional VaR based on Cornish-Fisher's expansion. Okay, so we'll take negative, multiply by mean return, plus the standard deviation times the standard normal variable. Okay, so there you go. So this is our conditional VaR based on Cornish-Fisher's expansion, which is of course greater than the one we obtained under the parametric VaR and conditional VaR. Now when we interpret the results under the Cornish-Fisher VaR, so we can see that based on the skewness and excess kurtosis that we have built in, over a 1-day period, there is a 1% probability that the loss will be more than 7.428%, and if the VaR is exceeded, then the average loss will be 10.026%.